So looking at the second spectra now, you can see, again, two sets of peaks. We have a different molecular formula though, all right? So you have four carbons and one oxygen, but you've only got two sets of peaks. So looking at let's look at the peak that's lower again, right? We got a peak down there at what, about 3.5-ish again. So in the same range, but it can't be now hydrogens on a carbon next to a bromine this time around. They must be hydrogens on a carbon next to an oxygen. So we know, again, that we can just go like this, and it's integrating to 2, right? So let's go put 2 hydrogens on there for now. Yes? How did you get to that point? I'm still lost. So you're looking at that chemical shift, and that chemical shift fits for hydrogens that are near an oxygen.
But why didn't you connect the oxygen straight to it?
Because that would have a different chemical shift. If you look at that chemical shift table, a hydrogen attached to an oxygen can land actually over a really broad range, if I remember right. Yeah.
Yeah, but how do you actually oxygen land in the same range?
It could, but it goes in a much broader range, right? Okay, so fine. We'll do what Julian wants. Yeah. Okay. Oxygen wants to have how many bonds?
2.
So, is that your molecule?
You made 1?
Because it integrates. That peak is integrating to 2 hydrogens. There has to be 2 hydrogens.
Oh.
So it's fine, but explore those possibilities. You hit a roadblock as soon as you want to do that. Or the only other way you could do this would be to say I have 2 oxygens with 2 hydrogens on it, and they're somehow connected. But your molecular formula says one oxygen. That's a no-go. Okay? So you can't make the integration and that chemical shift work. So you look for another option, which is hydrogens on a carbon next to an oxygen. I'll let you in on the secret. When you're looking at a hydrogen and an oxygen, it's very elusive. Sometimes you see it, sometimes you don't. It really depends a lot on the solvent you use for the NMR. So you need to don't overanalyze a hydrogen on an oxygen. Okay? Don't overanalyze that part. I got one. I'll show you one here as we flip the page. But I did this one first for a reason. So I'm looking at, just like with the bromine there, right? Similar range, everything looks the same. Why not just say hydrogens next to an oxygen? Integrates the 2, I can make that work. Now, my next peak. Up around 1 again. And there's 3 of them. So again, I'm seeing, right, Lane? I'm seeing that pattern again. And I can even look at the splitting. And I can see that this one is 4 and that one is 3 again. That same pattern is there. What's the problem?
You're missing half the molecule.
I'm missing half the molecule, and I can't add more oxygens. If I can add more carbons, I can add more hydrogens. So what happens here is, well, there, I add more carbons. What would happen if I added the carbons out here?
They would be even farther away.
I would lose 3 here, and I would lose, and the splitting would be different. So that would change the splitting, and it would change the integration. And yes, you're right. Now, if I add more carbons out here, they'd all end up landing around 1. This is when you see a lot of peaks landing in the same area, is when you have a long extended chain. I did not pick octanol for any of you to analyze by NMR. Because by the time I get 8 carbons in a row, there's at least 7 of them that are all landing on top of each other. All the hydrogens and all 7 of those carbons all land on top of each other. That's when you're starting to write out multiplet. it looks like a mess. Hard to really analyze. Anyways, so I do this, and I've got to get 5 more hydrogens from the molecular formula. Maybe I go here, but the integration says 2 and 3. I did that on purpose because I can actually set that integration. It's relative. Integration is relative. It's saying that one peak has 2 to 3 ratio, which is the same as 4 and 6, because actually let's do these are the same distance from the oxygen, right? As well as these are now the same. So when your molecule has enough symmetry, you'll end up having basically duplicates, and your integrations will double. All right? So with the integration, I wanted to give you that one little warning that in integration, be very careful of whether you don't have symmetry in your molecule. The way you'll know that your molecule has symmetry is if the number of protons added up from your integration is less than the number of hydrogens in your molecular formula. You catch that? So look at your molecular formula here for that one. You had 10 hydrogens. But if you add up all the integrations for the hydrogens, you had 5, meaning you know everything's double. Yeah? If it was 15 to 5, I would have said everything's tripled. I don't know where I actually see that, but okay.
Were you counting the integrations?
The integrations are below the peak. Sorry, let me point that out. The numbers above the peaks are the computer program actually giving you what their chemical shifts of each peak is. So it's giving you the literal chemical shift versus you just trying to see it. And then below the peak in this program is the integration. Our program, I think the integration kind of runs off to the side of the peak. And sometimes it's really hard to get to show off, but it'll be there. All right, let's flip to the next one. What's the next one? Yeah, actually, I have C2H6 in my notes. This is a two-page one with the IR. Yes, this one is. So look at the one that's got a 3 on it, right? So the one with the 3 on it, and on the back side of that is the IR for that NMR, given this molecular formula. Okay. I would say look at the IR first. Now that you're kind of experts on IR, what might you pick out of this IR spectra that's really super glaring, obvious? That big, broad peak there is about my best example I can give you of an OH peak. Man, when you have an OH peak, they're really pretty obvious. They're going to be big and broad and landing right around that 3200 range. In this case, it was 3347. I'll take that. So that tells me, see, and that was the harder thing about the last two. Without an IR of those, right, you're guessing a little bit as to what types of bonds are present. Now with IR, coupled with my NMR, I know a lot more. Right now, I know this molecule has an OH. I can also look over here and see that there's nothing at 17, so there is no carbon-oxygen double bond. So I know I have one oxygen from that molecular formula, and what I know right now, single bond. Oops, sorry. Let me get back to black. Back to black. So yeah, back to black. To help to answer really Julian's question, right? One of the ways I'll know, look at the IR. That's when I know I have an OH. And whether or not I see the OH in the NMR or not, if I saw it in the IR, I know it's there. All right, now looking at the NMR, notice this one now has 3 peaks instead of 2. And you can probably see that they're in similar kinds of ranges, right? I got something down here at about 3.5 again. I got something up here in the 1, closer to 1. But I got a new additional peak. Now, we've already kind of done some chemical shift. I'm going to say jump right ahead. Look at the integrations underneath those. We got a peak at about 3.5, integrating to, what do you think that tells me? Two hydrogens on a carbon next to the oxygen versus this one, right? That's not integrating to 2, that's integrating to 1, which, lo and behold, oh man, back to me, machine. There we go, okay. Look at the next peak there at about just 2.7, 2.8. You see that? It integrates to 1. Found it. Because now what am I left with? From that molecular formula, I need 1 more carbon and 3 hydrogens up here around 1, integrating to 3. Oops. So yes, I am trying to show you a pattern where you see that ethyl group when it's next to a bromine, when it's next to an oxygen in ether, when it's next to an oxygen in ethanol, alcohol, right? I got one more to throw at you here too. Notice the H on that OH looks kind of like a singlet, but look what happened to the quartet for the 1 and 3.5.
Then let's go.
Yeah, you know why? That hydrogen is neighboring. But because it's on an oxygen, it's a really finicky one. The bonds are weaker. The oxygen-hydrogen bond is much weaker than a carbon-hydrogen bond. We can break a carbon-oxygen, we can break an oxygen-hydrogen bond far, 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 far more likely than a carbon-hydrogen bond. So because of the weakness of that and all that kind of great stuff, it's kind of hard to capture. And so you get a much weaker splitting due to that one, but it's different than those 3. So what you're really seeing are 4 peaks split into a doublet by that other hydrogen, and they just kind of shift slightly over, so they're kind of right on top of each other, and they look like that, unfortunately.
I still don't understand splitting what that is.
So yeah, again, no, let me do it this way. One of the things that people do is, so take for example these hydrogens, and we'll say, okay, they could be spinning up, let's say. But now when I come over to these 3 hydrogens, now relative to that, they could be splitting down. All right. And I think they take all the hydrogens all together, and I can't quite do this real well, but what that's one possibility, that these are down relative to that hydrogen. And actually you can do it, let's say all 3 of them are down relative to that one. Well, another possibility is relative to that one, they're all up, right? That could be a different combination. Or you could have 1 down, 2 up. Or you could have like that, right? And again, I'm not doing it real well, but when you look at the probability of how these spins align or misalign, the misalignment is going to be essentially pulling your magnetic field in the opposite direction, versus when it's aligning, it's enhancing it. And so you start to see these subtle shifts in your signal due to that neighboring nuclei, whether it's relative aligned with or against in a relative sense. when you think about all the probable ways that these things can align, you end up with 4 possibilities, or sorry, I should say 4 examples where their energies are different. You might argue that this and this with, no, sorry, these two would have the same energy, same number up versus down, right? So those two have the same energy, they overlap. In terms of different energies, you end up with 4 when there's 3 neighboring hydrogens. You don't have to think about that every time. I'm just saying use the n+1 rule. In the n+1 rule, here, these 2 hydrogens are identical. On the next carbon over, there's 3, which makes your n 3. So you'd expect these to be split into 4. In this case, I didn't say it had to be on a neighboring carbon. It could be a neighboring atom. Since there's a hydrogen on this oxygen, this can also split. It doesn't split the same way as these 3. So rather than making my n 4, it takes the peak of 4 and splits it n+1, 2. So you get 2 sets of 4 that are very, very close and overlapping, and that splitting gets much more complicated. So what I would tell you is, this is why I say, when you're analyzing your structure, get the chemical shift first and the integration right, and there's really only one way you could have drawn that, whether or not the splitting made any sense at all. Okay? You'll end up with the right answer, even though the splitting looks crazy, because there are going to be examples as we go on where the splitting can be really, really nonsensical. We give you the idealistic perfect world version. Well, it's always n+1. The one I can't show you, and I won't even give you it as an example to run for an NMR, it won't be on the final exam, when it's cyclic. Cyclic structures really mess things up, because we haven't even gotten to talking about equatorial and axial yet, and there are 2 hydrogens on the same carbon. You'd say, oh, they should have the same chemical shift, and they don't. And you get wild splitting as a result of that. So I don't want you guys obsessing too much about splitting. There are scenarios, like in this case, right? In this case, this one still splits into a triplet because all it has are those 2 hydrogens. So you'll still see that triplet there. Okay? Yeah.
Can you do what you did in the first one and like circle which?
Oh, when you analyze a spectra, it is good to associate particular hydrogens with particular peaks. And so there's 2 things you could kind of do here. You could number or letter. Some people will call these like HA and those B, and maybe just call this the OH, kind of thing, something like that. And then on each peak, you'd say, okay, this OH you'd associate with the peak at 2.8, 2.77. You'd say the peak that you're seeing at about 3.5-ish there again, you'd associate with these HA protons, or say that they indicate the HA protons. And then finally the one up around 1, you say are associated with the HB protons. I don't care how you label it, or if you like to draw arrows, that's perfectly fine. You can draw lines that connect. But yes, that's one set. That's a different set. And that's all by itself. So one trick here is being able to identify all the hydrogens that are the same and all the hydrogens that are different. With that, let's try to switch to numero 4. I learned last night the Spanish word for avoid. Evitar. Yeah, I didn't know that. I've never had to avoid things. in Spanish. But now I wish I knew that word more often. Vita responsabilidad. Yes.
All right.
That's the adult movie. That's what you call retirement. Okay, for this one again, looking at you got a molecular formula. See how it's fairly similar. Sorry, they're coming and giving me a new water softener today. I don't know why they called me right now. Okay. So molecular formula. I would go to the IR on the back for that one. And what do we notice in this IR? Unlike the last one, yes, but nothing in the OH, right? So I am not going to put a hydrogen on an oxygen here because it's not in my IR. But I do have that carbon-oxygen double bond stretch in there. So, well, you can start there. Say, whoops. Colors. Okay. You can start by drawing carbon-oxygen double bond. Right? Now, when we look at the, on the IR, stretch right there at 1700, a big peak at 1700. Whenever you see a good peak in the IR around 1700, you know there has to be a carbon-oxygen double bond. Because that's just CHs. And just about everything's going to have a peak there. So it doesn't really tell me much about my structure. It's just like, yeah, it's organic. I'm not giving you something inorganic. You're going to see carbon-hydrogen bonds. You can guess that much. All right. So yeah, the big things here are like carbonyl or the OH. I got some other fun ones with triple bonds in them. All right. Now coming over here, how many peaks we see on this one? About 3, right? And guess what? We're also seeing a pattern of quartet, triplet, right? The quartet now, though, is down around 4, right? Down around 4. I will tell you this, anytime I see a peak around 4, I am typically looking for an ester. I'm looking for an ester. If you look at your chemical shift table, hydrogens on a carbon next to an oxygen, hydrogens on an oxygen next to an ester here, these are almost always right around 4. Kate's gotten to see that quite a few times, except it's not this, it's a methyl. So we tend to see a big singlet around 4. That's our ester. We know that every time. It's always there right around 4. It shifts a little bit here and there, whether it's next to a double bond or something else like that. But okay, so this case, there's my CH2. But now to get to my pattern of CH2, CH3, to get my quartet triplet pattern again, well, here's this one, also up there again, right around 1. That doesn't change much. All I've changed is what's pulling electrons away, but that doesn't really shift this one much. You notice that? Look through all those examples. You can see that this part doesn't move that much. I'm just changing what I threw out here. Right? So this is actually very similar to ethanol, except now with that carbonyl there. What's that third peak? Oh, and by the way, if you look at the integration of 2, integration of 3, right? We see that pattern. Third peak showing up closer to 2, and it's got an integration of 3. There's 2 things that I look for when I see hydrogens around 2. If I see a peak around 2, most of the time they're hydrogens on a carbon next to a carbonyl. Ketone, aldehyde, amide, ester. You look at them. I give them all as different examples there. You look at hydrogens in red that are on carbons next to carbonyls. and they're almost always around 2. You just follow them right down, okay? So 3 hydrogens on a carbon next to the carbonyl, and add them up. 4 carbons, check in my molecular formula, right? 8 hydrogens, check on the molecular formula, and 2 oxygens. Boom, got it, right? Just from chemical shift and integration. If you want to look at splitting, this one, again, quartet, has got 3 hydrogens on the next carbon over. Nothing to this side this time, so that's not messing it up anymore.
3.
This one's 3, because there's 2 on the one next to it. How many hydrogens are on the carbon next to this one?
0.
So what happens when my N is 0? I get 1 peak, a singlet. Methyl groups that are attached to something that has no hydrogens. Methyl groups attached to something with no hydrogens will always give us a singlet. Always give us a singlet. All right? That's the only time you're going to really get singlets. So that matches for ethyl acetate. The IR gave us the carbonyl. The NMR told us the types of hydrogens we have and what they're next to. And we can end up with that chemical structure for ethyl acetate. To emphasize why, one of the things I said already, but I'm just going to show this to you. Looking at 5. NMR looks simple. It's not. Flip it over. Look at the IR. In the IR, there's really nothing other than carbon-oxygen double bond around 1700. We're getting my molecular formula. C6H10O. I know from the IR there must be this. I'm now trying to figure out where are my other 5 carbons. And who's looked at the integration yet? What's it add up to? 5. How many hydrogens do you have? So I must have symmetry.
But you're missing a part.
I can't go symmetric and be linear with 6 carbons.
Oh, it's a ring.
It's a ring! Oh, you say. Okay, let's try this. Oh, what is going on? Okay, there we go. If you can't make it symmetric, put a ring on it. Oh. Now, look at the hydrogens on this carbon, identical to the hydrogens on that carbon. Where would we expect chemical shift? Around 2, because they're next to a carbonyl.
Whoa.
We see 2. Around, we see a peak integrating to 2, close to 2. And now that one, if you look at the 2 hydrogens there, they're next to a carbon with 2 hydrogens, and it does actually look like a triplet. It does look like a triplet. It fails when we go beyond it. Now, looking at these 2 hydrogens, they're identical to those 2 hydrogens. And now you say, oh, it's neighboring. Nah. That's when it's a no. You can look at that peak, and if you can pick out 4 plus 1, 5 peaks out of this, God bless you. I don't see it. Now, chemical shift though, right? You can see how these 2 are quite close to each other. How do I know which one's this and which one's that?
The one opposite.
This one integrates to 2, and that one integrates to 1. which is really a 2 to 4 to 4 ratio, excuse me, versus a 1 to 2 to 2 because of the duplication here. So this has to be the peak that's integrating to 1. This has to be the peak integrating to 2.
Blessing.
Something in the room's getting to me. I probably signed to stop. Oh, all right. But now when we look at that splitting, this is not really 5, and this one is not really 5 either. All right. Here's where this gets really wild. We're going to eventually talk about how chair, 6-membered rings have 2 chair forms, especially in the cyclohexanone. It's doing this rapidly in the NMR. And so those protons that are axial and equatorial are changing rapidly between the two. It's much more pronounced for these guys down here than these. And since these two are different than those two, it does not work as n plus 1. It's making a triplet of triplets. I argue it's making it even worse than a triplet of triplets. How do you take 3 peaks and make it 3 peaks on top of 3 peaks on top of 3 peaks? It's even worse than that. It's probably these two are never identical. And so this one causes different splitting than that one. And that's because one's equatorial, one's axial. So you're really getting a doublet of a doublet of a triplet. And it doesn't move that much. It's all on top of each other. That's where I would call that a multiplet. So once again, Julian, does the splitting tell me that structure? I can get it from the molecular formula, the IR, and that integration. Just by looking at chemical shift and integration, that's the only way I could put that molecule together, even though the splitting got really wild. Yeah? All right. One of my favorites. Let's look at number 6 here. Number 6. I'm going to start putting some of the pressure on you guys. What do you see in the IR? Yeah. Any of you see an OH? No? Now there's some things. Yeah. Anyway, when I see this, weak in the carbon-hydrogen bonds, aromatic. You don't need to necessarily see that in the IR. You can probably get it from your molecular formula. There's a thing called degrees of unsaturation. So for saturated carbons,
All the hydrogen.
have 2n plus 2 hydrogens. 2n plus 2 hydrogens. Okay? If you have something less than 2n plus 2 hydrogens, then you have what we call a degree of unsaturation. I never remember the equation for degrees of unsaturation. I know that if I have a halogen, okay, you have to subtract a hydrogen. In other words, a halogen is going to replace a hydrogen. An oxygen, think about that, doesn't technically replace the hydrogen. If I put an oxygen on there, it's an OH instead of an H. I still have that one hydrogen. I just added an oxygen. Replace the hydrogen with the nitrogen. It's going to be an NH2. So I would add a hydrogen for every nitrogen that's in that structure. Worrying about sulfurs and phosphorus and all that kind of stuff, I don't think that's very practical. So what you do to define degrees of unsaturation is you take your 2n plus 2 and subtract 1 for every halogen, add 1 for every nitrogen. Do we have any of that in this particular molecular formula? No. So for 2n plus 2, for n carbons, I should have said the n is carbons. We have 8 carbons, right? So we would have 2 times 8 plus 2, and then you always divide by 2. Always divide by 2. So that means this one's going to be 1618 divided by 2. I think I did that right. I feel like I'm missing something. What am I missing?
Why do we have to divide?
Why don't you just make it n plus 1?
Is it n plus 1? No. I think it's 2.
But like you just divided by 2.
So this gives me 9. Hold on, let me think in my head here. I need to get 7. Why am I not getting 7? Did I do something wrong with my math? I know I'm doing right. 18 is what I should have gotten. But we have how many?
How many were?
8. So subtract 8 and then divide by 2.
Wait, what are you?
So if it was saturated, it'd be 2n plus 2, making it 18. What we actually have in the formula is 8, giving me a total of 10. Dividing that by 2 gives me the number 5. 5 is my degrees of unsaturation. So the difference, difference between saturated molecular formula and the actual molecular formula. If I have something less than 18 hydrogens on there, it means this molecule is no longer saturated with hydrogens, it has unsaturation. Each unsaturation takes off 2 hydrogens. Okay? Each unsaturation takes off 2 hydrogens, that's why we're dividing by 2. So follow this now. What is an unsaturation? Double bond. If I added the double bond to the molecule, that would take 2 hydrogens out of that. Whether it's carbon-carbon or carbon-oxygen, you're going to lose 2 hydrogens for every double bond.
Yes.
You just got to believe me. I've done the math. Okay, that's what it is. Every time you get a double bond, you're going to lose 2 hydrogens. Every ring takes off 2 hydrogens. So this degree of unsaturation, I slid that somehow, or like, whoa, expanded it. Oh my gosh. Stop. There you go. These degrees of unsaturation tell me how many double bonds and or rings I have in the structure. Anytime my degrees of unsaturation go above 4, I'm going to look for a benzene ring because there's 1 degree for the ring and 3 for each double bond in the ring for a total of 4. What's my 5th one for this molecule? We already talked about a carbon-oxygen double bond. I'm just going to arbitrarily stick it out there for right now. Now looking at the NMR, yes?
So instead of doing all that, we have just looked at
Yes. Yes. You do not have to do degrees of unsaturation. The biggest thing that I would say is when you see way too few hydrogens, clue into maybe I've got some double bonds and rings. And when it's really low, it's probably aromatic. Now, looking at the NMR. So, IR I said aromatic ring because the CHs were low. When this peak for the CH is low, I think aromatic. I could have looked at the molecular formula and it would have suggested aromatic. But boy, oh boy, look at this NMR. I'm going to draw your attention, first of all, to now we have peaks around 7. Looking at your chemical shift table, there is really only one thing that ends up showing around 7. Hydrogens on a benzene ring. Okay? Sometimes Sometimes hydrogens on alkenes, hydrogens on a carbon-carbon double bond might get close to 7. Might, not always. They're more often 5, 6, and then maybe a 7, 6, 7. Oh, sorry, had to slip it in there. Most of the time, you see something at 7, it's think aromatic ring. So we could have looked at the IR, saw the weak CH. We could have looked at the molecular formula and said, ooh, aromatic. But boy, oh boy, look here. If I see that, draw me a benzene ring. Okay?
Yes, sir.
The other one on this that sticks out like a really, really sore thumb.
Is the hydrogen attached?
Hydrogen around 10. Anytime I see a hydrogen around 10, absolutely always an aldehyde. The hydrogen on a carbon next to that's on an aldehyde. This hydrogen here almost always T10 ppm, and what's next to it? No hydrogens. It's always a singlet. Really sharp singlet shows up right at 10. Boom! I know I got an aldehyde. You'll never miss it. The one, I'm going to tell you one other one that's on that chemical shift table that I have a really hard time ever seeing is a carboxylic acid. The H on the OH of a carboxylic acid supposedly is in this 15 to 20 range. At best, they show up as this like weird sloping broad bump in the baseline, and they never give me a very good peak. Never. So I never look for the carboxylic acid, but boy, that aldehyde will show up every time. Okay? So we know we have a benzene ring, and we know we have an aldehyde.
We're missing.
And I'm putting all that together. So what am I missing?
Or more than.
An oxygen and a carbon and 3 hydrogens. All right? Now, do I want to put the oxygen in here somewhere? I certainly don't want to put it, I cannot put it between here. I go to a carboxylic acid, right?
We already, there's only one oxygen.
Oh, okay. So I don't have another
There's
oxygen.
still a methyl on the other end.
I'm thinking of a different structure. I'm not going to tell you what. So there is no other oxygen.
Oh,
So there's no other oxygen, but if there was an oxygen, you wouldn't put it in here and all that kind of great stuff. You would look for where your hydrogens are. You've got 3 hydrogens left. You got 1 peak to consider. It's up around 2, which is when we see hydrogens on the other option here is when you see hydrogens on a carbon next to the benzene ring will also show up at 2. Hydrogens on carbons next to ketones, aldehydes, next to the carbonyl, or next to the benzene ring will show up around 2-ish. Here, integrating to 3, and it's a singlet. There's no hydrogen here. Oh, so that fits. What if this singlet of 3 was down around 4, in between 3 and 4? Then I'd have another oxygen in there, and I would put it between here and there. Because now it's hydrogens on the carbon next to an oxygen, not the benzene ring. Let me explain the splitting here too. Look at how symmetric this benzene ring is when these 2 groups are opposite. These become identical, and those become identical. And in this case, they do behave. This hydrogen is next to 1 with 1 hydrogen, therefore split into 2. We see something that integrates to 2, split into a doublet. That's a pattern on aromatic rings you will see when they are opposite each other. In contrast to, I know you want me to just erase all that ugly degree of unsaturation thing. It has to be this relative to that. Because look what happens here now. This hydrogen is not the same as that hydrogen,
No, you would have 3 different.
right?
peaks.
You actually probably have 4.
Watch it.
4. These two will be very close to each other often and kind of overlap. What's the other option I have?
You could put it not all the way, but yeah.
Now looking at this one should show up as a singlet almost. Here's where benzene rings are annoying. Sometimes this one won't be a singlet and it'll actually get split by this one over here. Aromatic rings will tend to go one further than they're supposed to. So again, I would not overanalyze the splitting, but it would look different here in the chemical shift. Here I'm going to see 2 peaks because of the symmetry. Here I would expect to see 4 peaks. Here, also 4 peaks.
Yeah.
Definite 4 peaks. This one down here again might get sort of, well, it's all by itself anyways. These two definitely would not be the same. All right.
Yay.
So I wanted to give you an example of a good aromatic ring in there as well. Let me show you maybe, what do I got time for? Yeah, let me show you 7 and 8 where I do not have IR for these because I pulled them off the internet. This is much more likely what you would see on an ACS standardized test. I find them annoying because they're really hard to read. They oftentimes don't give you the integration. They oftentimes don't even give you the peak picking. And I'm like, who does that, right? You know, you kind of, I had to draw them in. I had to draw the integration in and then put the integrations on there because all it did was give you the spectra. And then you have to kind of imagine what the actual ppms are. All right. So without the IR, just from the molecular formula, anybody want to start to see, what do you see on this, let's say, spectra right now?
I have a feeling we have OH bond.
You think you have an OH bond? You would be incorrect.
Oh.
Look at this peak here. Where does it land? Bound 4. And so that's going to be hydrogens on a carbon next to an oxygen. That is typically an ester. So I'm just going to automatically guess I have an ester, in part because I have 2 oxygens. All right? Only because those hydrogens are at 4. If they were at 3, I wouldn't say ester. I'd say ether. I'd put that other oxygen somewhere else. Okay?
Why is it?
So hydrogens on a carbon attached to an oxygen that's part of an ester tends to be around 4. Hydrogens on a carbon next to an oxygen that's part of an ether tend to be 3. You're not going to find that in the chemical shift. I'm just telling you. I'm giving you 2 examples, by the way. If you look at ethyl ether versus ethyl acetate, let me refer to it. Okay, let's go back. Look at carbon. Look at the spectrum number 2. Right? Spectrum number 2. That is hydrogens on a carbon next to an oxygen that's not part of an ester, just an ether. 3.5-ish or so, right? When we went to, I believe it was 4, looking at number 4 now look at that same hydrogen. That's now hydrogens on a carbon next to an oxygen that was part of an ester. Look where it is. It's around 4. See my point? Your chemical shift table can tell you a lot of things, but I'm telling you right now, if you see a hydrogen around 4, you've got to look for an ester. Could be wrong, but more often than not, you're looking for an ester. All right? You got 2 oxygens in there you got to use somehow, so go looking for an ester. How many hydrogens are on that? See 2? So I'm going to put 2 hydrogens there. So what might be on the other end of this? Of that carbon-oxygen double bond. Anybody see that? Anybody see the big singlet? It's got some junk at the base of it. But that's when we end up having things that overlap. Okay, so you have a singlet overlapping with something that's got more splitting to it. Look at the integration for it as well. 4. How do you get a carbon with 4 hydrogens on it? Or do you have 2 things? You have a peak integrating to 1 and a peak integrating to 3. So you can maybe you can now start to see you got a singlet in the middle of more peaks. And that singlet's probably 3. Nope, it's around 2. See, it's around 2. Hydrogen's on a carbon next to a carbonyl. Yeah? Now let's try to figure out the rest of this. Notice this is split into how many peaks? 2. Meaning the next carbon over must have how many? Just 1. How do I get that? Let's look, and I'm cheating here. I'm looking at splitting and I really shouldn't. Look at the peak at around 1. What's its integration?
6.
How do you get 6? Without symmetry. 2 methyl groups that are identical now give me 6 total hydrogens. And look at their 1, right? So we expect them to be all the way over there. And where was this 1? Underneath that singlet. You see how NMR can get tricky pretty quickly, right? But now, just from chemical shifts and integrations, I think you can get very close to the structure. Anytime you see a peak integrating to 6, look for a dimethyl something. A dimethyl something. Right? If I had a peak that was a singlet and integrated to 9, change this to a methyl. That's that tert butyl group or dimethyl ethyl group. If you had 3 methyl groups out here, then this one no longer has a hydrogen, not split by anything. It's just a singlet and it integrates to 9. Anytime I see a sharp singlet integrating to 9, I know I have that pattern every time. Okay? The other part of this that I really want you to be able to see. I'm sorry, I got to miss this. Hello? Yes. Yes. They should be there. Yeah. Yes. Well, that's my truck. But did you not? Did you knock on the door? Okay. Let me. I'll try to get. I'll tell them that you're there. Okay. Yep. Bye. That worked, dude. Okay. He must have called the other time. They were supposed to come between noon and 5. That first phone call was before noon. Don't make me mad. Cable companies. This water softener guy is. All right. So anytime, what I want you to see in this pattern is if you look at this one up here, that peak of 6 is a doublet. So it's integrating to 6 and it's a doublet, 2 peaks next to 1 hydrogen. So if I see something integrating to 6 in a doublet, I'm always looking for what we call more that isopropyl group, right? But now look at how's this one going to split? Split by 6 and 2? Can't count that high. You see weird doublet thingy splitting underneath there, and that's where you're not going to overanalyze that splitting. Okay. You see something similar here on 8. Okay. Something similar here on 8. See the doublet of 6. You got a singlet of 3, and then you've got this wild peak there, a bunch of peaks. Molecular formula is C5H10. I know you can just see this right now. I'm feeling rushed and harried by that phone call.
I have one more question about 7.
Yeah.
So, like the 2 H3s on the left are for that first peak at 1, but then
Yep.
the second and third peak, which hydrogen's on.
This is overlapping with that one over here. So you're seeing a sharp singlet for this one, and a bunch of peaks kind of right in the same area that are much smaller. Yeah, tricky. This one does the same thing but separates it out. So if you notice there on 8, again I'm seeing 6 split into a doublet. There's 1 H here. Still up around 1-ish. I've got a sharp singlet around 2 next to a carbonyl. I've only got 1 oxygen this time, not 2. So now look what happened to that H. It did separate from that singlet, but now you're seeing all the little peaks there. See that pattern? Yeah. So anytime I see a doublet with 6 and followed by a whole mess, I'm generally looking for that type of a group somewhere in the molecule. All right. I am going to leave it there so I can deal with this water softener guy. 9 and 10 are a little bit trickier. I'll say one thing about 9 real quick. 9, these 2 peaks down here, I did this to give you an example of a spectrum that has hydrogens on a carbon-carbon double bond. So this is coming from an alkene. So I wanted to give you examples of different things. This is one with an alkene. 10's mean. 10's got an epoxide in it. I mean, I like it, but I just didn't. You're not going to deal with too many epoxides. All right. So what we'll do is we will take those NMRs next week while we're doing the next lab, and I'll give you a couple of weeks to work on solving those NMRs, coming and asking me questions. We will be taking more NMRs as we go throughout the semester on the molecules we're running. Some of them get pretty wild, and so you got to be able to pick out meaningful peaks of them to help support your final conclusions. Okay, but this is a learning process. We're gonna keep working on it together. Okay. I know that's kind of intense, but just remember, chemical shift first, integration second, maybe splitting, but that gets hard.
Do we get IRs with it?
All these would probably get IRs. There may be a few examples of experiments we run where we don't take an IR, but you'll have like a melting point or a TLC or the DC mass spec.
I don't think I can just look at it and be like, oh yeah, it's.
I don't ever look at an IR and just say,
Well, no, just the NMR.
Oh, the NMR. Well, yeah.
Like, oh yeah, it's this one.
Hey, listen, the other thing about NMR is it's not coming in a vacuum. You know what reagents you used.
Yeah.
So you know the things I started with probably going to be in the end. And oftentimes I will give you an NMR of the starting material for comparison. All right? Cool.